Hello, welcome to another lesson where we are going to study what happens when a particle that is charged is moving under the influence of an electromagnetic field. Okay, and in the first lesson we showed that the Hamiltonian of that particle is equal to 1 divided by 2m p minus qa squared, and then plus q phi, where here q is the electric charge, then a is the vector potential, p is the linear momentum of the particle, of course, and phi is, well, the scalar potential, where these things are related with the electric field as minus the gradient of phi minus the partial of a with respect to time. And then we know that for the magnetic field we have that this is the curl of the vector potential A. Perfect. This is what we showed on the first lesson talking about this topic. So what we are going to see now is that, well, we are going to think that this particle that is charged, and remember, well, now is going to be only on the influence of a magnetic field, okay? There will be no electric field in this example. So this means that this quantity here is going to be equal to 0, and for that to happen, well, we need this quantity to be 0. But looking that we are going to be working with a magnetic field that is uniform, well, it doesn't change on time, so that means that the vector potential will be, well, the derivative with respect to time of the vector potential will be 0, and we will have that minus the gradient of phi will be 0, giving us that phi is going to be a constant element. Okay, so remember that when you have a Lagrangian or a Hamiltonian that is, for example, well, some function here and then plus a constant, well, we can just ignore that constant, because when we take this into the Hamilton equations, this constant will not play any important role. Okay, so looking at here, we will have a constant because it multiplies q. Then we can just set this phi to be equal to 0. Okay, so this element is going to disappear, just for our purpose. Okay, so that means that the Hamiltonian of an electric charge that is under the influence of a uniform magnetic field is equal to this thing that I have here, right? And this is squared. Okay, perfect. So we are going to consider the example when the vector potential can be defined as 1/2 V0 K cross R, right? Okay, in this case we are setting that the uniform magnetic field is of the form V0 K in the Z direction, and, well, of course V0 is just a constant. Okay, and the vector R is the one that points to the particle, of course. So that means that to calculate the vector potential that we have here in this expression, well, we need to calculate first what is this cross product. Okay, so that means that, well, A is going to be equal to 1/2, and then let's say I, J, K, and then we will need to write here the components of the magnetic field, but we can see here that we only have one component for the K. So here we have 0, 0, B0, and then for the R will be X, Y, Z. Perfect, so this is going to give us I times minus YB0, and then minus J, that is going to multiply minus XB0, and all this is divided by 2, right? So we will get that the vector potential is going to be on a different notation. Let's say that this is minus YB0 divided by 2, and then this will be XB0 divided by 2, and the K component will be 0, of course. Perfect. So we have found the vector potential to take it into this equation that we have here. So this is going to lead us to have that the Hamiltonian is going to be 1 divided by 2m and then p, but p we can define it as px, py, pz, right? So if we make the subtraction, what are we going to get? Because right now look at here, we need to subtract these quantities, so we still need to multiply by q the vector potential. So we will get px minus, actually plus, right? Because it's minus times this minus will be a plus, qyb 0 divided by 2, and then py minus x minus qx be 0 divided by 2, and then we will have here only the pz element, and then this vector we need to raise it to the second power. Okay, so after doing this, we can just take the components square like this. It will be 1 divided by 2m, and then this quantity px plus qyb0 divided by 2 squared plus py minus qxb0 divided by 2 squared, and then plus pz squared. So with this, we have an expression for the Hamiltonian of a particle, a charged particle, that is moving under the influence of a uniform magnetic field. Okay, perfect. So looking that we already have the Hamiltonian, with this we are going to be able to construct the corresponding Hamilton-Jacobi equation. So we are going to use a function s that corresponds to the transformations pi equals the derivative of s with respect to qi, and qi equals the partial of s with respect to pi. And recall that this is the canonical transformation, well, the generating function that we have been using in recent lessons. So with these rules, we can construct the Hamilton-Jacobi equation because px is equal to the partial of s with respect to x, of course, py is equal to the partial of s with respect to y, and pz is equal to the partial of s with respect to z. Okay, perfect. So what will be the Hamilton-Jacobi equation? Well, we will have 1 divided by 2m, that is going to multiply px, but that is the derivative of s with respect to x, and then plus q. And I'm going to switch the q for an e to express the charge, the electric charge of the particle, just for not to get confused with this little q that I'm using here, right? So let me write plus e y b0 divided by 2, all this is squared, and then plus the partial of s with respect to y minus e x b0 divided by 2 squared plus the partial of s with respect to z. This is squared again, and then we will have plus the partial of s with respect to time equals to 0. Yep, this will be the Hamilton-Jacobi equation for the corresponding particle. Okay, so this is the Hamilton-Jacobi equation. How are we going to solve this? Well, we have been using the method of separation of variables in recent lessons, but you should notice that this method is not going to work out with this example. But we can construct a Hamilton-Jacobi equation corresponding to a different function that will be able to be solved with the method of separation of variables. Okay, so we are going to make a change of variable. To do that, we are going to propose that s tilde equals s plus e b0y x divided by 2. Look that with this, we will have that s is equal to s tilde minus e b0 yx divided by 2. Okay, perfect. So recall that, well, we need to take the partial derivatives of the new function s tilde. So we will get that the partial of, let's do it with this equation, right? The partial of s with respect to x is going to be the partial of s tilde with respect to x, and then the partial of this with respect to x. But that is going to be, of course, minus e b0y divided by 2. Look that what we have done is to generate a new function that, it has the minus e b0y divided by 2. And then when you substitute the value of the partial of s with respect to x, well, we will see that this element will be cancelled with this element, so we will only get the partial of s tilde with respect to x, right? Perfect. So, what happens if we calculate the partial of s with respect to y? Well, we will get that this is the partial of s tilde with respect to y, and then minus e b0 x divided by 2. Okay, perfect. And then just to finish, well, the partial, let's do it with orange, the partial of s with respect to z, it will be the partial of s tilde with respect to z. And the same thing happens with the derivative with respect to time, right? Like this. Perfect. So we are going to take these results into the Hamilton-Jacobi equation that we had. So this is going to give us 1 divided by 2m, that is going to multiply, well, the partial of s with respect to x, but as you can see, this is just the partial of s tilde with respect to x squared. Again, this element cancels with this element. And then plus the partial of s with respect to y, which is this what we have here. So it will be the partial of s tilde with respect to y minus e b0x divided by 2, and then this element that we have here, right? So it will be again minus e b0x divided by 2, all these squared, and then plus the partial of s with respect to z, but that is the partial of s tilde with respect to z, like this, and then plus the partial of s tilde with respect to time equals to 0. Well, it is very easy to notice that this quantity is only going to be minus e b0x, right? Perfect. So as you can see with this, well, we have a new function that is going to be, a new equation that can be solved with the separation of variables method. In the first Hamilton-Jacobi equation here, recall that here, well, we have the derivative with respect to y, and then a function of x. And then here we have the derivative with respect to x and a function of y. But in this case, here we only have the derivative with respect to x of some function, and here is where we have again the derivative with respect to y of that function and a function of x. So this thing has changed and now is easier, such that it can be solved with the separation of variables method. Recall that the separation of variables method wants to propose a function s that depends on functions that are only of one variable, right? So for example, let's say f1 of q1, f2 of q2, all the way up to, well, the total generalized coordinates that we have and the time, right? So the thing here is that we are going to propose a function s tilde that is going to be a sum of functions of just one variable, like we mentioned here. So how is this going to be? Well, the first thing you need to notice is that in the Hamilton-Jacobi equation that we have here, we have only the x explicitly in the expression, right? It is over here. But we do not have the y, we do not have the z, and we don't have the time, okay? So remember that we have been working with these equations, and we say that when we are using the method of separation of variables, if the generalized coordinate do not appear in the Hamilton-Jacobi equation, we can propose that the function corresponding to that generalized coordinate is going to be a linear function. So what I mean with this is that, for example, looking that the y doesn't appear in the Hamilton-Jacobi equation, we can propose that the function for y will be a linear function of the form p2y. Okay, And then it will happen the same with the z. We can propose p3z. And then with the time, we are going to do the same. And this, well, in this case, remember that we have been doing the proposal as minus p1t. Recall that we use the minus sign because we usually take this partial derivative of the time to the other side of the equation, and with that minus we can get a plus there. But that is not important. Actually, we could propose plus p1t and nothing happens, right? The thing here is that the only function that is going to be variable is going to be the function that corresponds to x, right? So it will be f of x. Okay, perfect. So this is going to be our proposal for the solution of this. So we need to calculate the derivatives corresponding to each variable, right? So the derivative of s tilde with respect to x is, of course, the derivative of f with respect to x. The total derivative, right, because this is of only one variable. And then the partial of s tilde with respect to y will be p2. The partial of s tilde with respect to z will be p3. And then the partial of s tilde with respect to time will be minus. Okay, perfect. So with this we can substitute into the equation to get 1 divided by 2m. It will be here the derivative of f with respect to x squared plus the derivative of s tilde with respect to y, which is p2 minus eb0x squared plus, and it will be p3 squared, right? And then it will be minus the derivative of s tilde with respect to time. But we know that this is minus p1, and this is, of course, plus p1. Perfect. So we have a new differential equation that is very easy to solve because we only have, well, to find the function f, and it depends on x. And looking that p2, p3, and p1 are constants, well, this is just a differential equation of the variable x. Okay, right? Yes, so it is very easy to solve. I mean that we are going to get that the derivative of f with respect to x squared is going to be equal to 2m p1 minus p3 squared minus p2 minus eb0x squared. So here's where we are going to make a stop to recall why p1, p2, and p3 are constants. Recall that we always propose a solution for the Hamilton-Jacobi equation S that is a generating function of canonical transformations. But recall that if a transformation is canonical, that means that the new coordinates generated satisfy the Hamilton equations. So that means that qi dot is equal to the partial with respect to pi of some new Hamiltonian k, right? Recall that this is analog to the Hamiltonian function. So the thing here is that we choose that this new Hamiltonian k is equal to 0. So this takes us to have that qi dot is equal to 0, making that qi is equal to 0. The thing here is that it happens the same with the other Hamilton equation, which is this, right? So if k is equal to 0, this is equal to 0, making that pi is, well, actually here's a constant, right? It could be 0, but in general is a constant. So it will happen the same with the upper piece. So that means, again, like that, well, p1, p3, and p2 are constants. Okay, so very easy to solve this differential equation. Again, we will have that the derivative of f with respect to x is going to be equal to, remember that this is plus minus, but for convenience we are going to choose the plus solution. So this will be the square root of 2m p1 minus p3 squared minus p2 minus eb0x squared, like this. And well, from here we can get that f of x is going to be the integral of, well, this whole square root that we have. Okay, perfect. So this is our function f that we needed to find to complete the proposal of solution that we made. Recall that we proposed s tilde as this whole thing, but well, this is a constant, this is a constant, this is a constant, and we have found f. So with this, we can construct the s tilde function that we wanted to find. Also, remember that s tilde is just a piece to get the real solution, well, the important solution that we wanted to find for the original Hamilton-Jacobi equation. So recall that to find that function, we need to subtract this quantity from the s tilde that we just found. Okay? So that means that if we directly construct that s, well, we will have that this is minus EB0xy divided by 2 plus P2y and then plus P3z minus P1t and then plus, well, f of x, right? But that is this whole integral that we have. It shouldn't be so hard to solve this integral, but right now we are not going to be interested in doing that. Perfect. So with this, we have found the Hamilton-Jacobi equation solution for the particle that is charged under the influence of a uniform magnetic field. I think that's a really long name for a physics problem, but that is what it is. Okay, perfect. So yeah, this will be the final important result of the lesson. I hope you enjoyed the video. And yeah, I think it wasn't too long than the previous lesson. Perfect. So I will leave you the link to the previous lesson where we showed this Hamiltonian, how to get to this Hamiltonian. Well, you can see it in the video that I'm going to leave you in the description of the video. Perfect. So what we are going to do in the next lesson is to actually find the equations of motion from this generating function that we found and to solve the equations of motion to see what is the solution, the final solution for the problem. So I think I will finish the lesson here.